All right, so welcome back. So for this week we have midterm on Friday. Okay, so I'm only going to be doing one lecture this week, plus practice midterm video. So let me just say this lecture will not be on the midterm. Okay, so the material is only the first 8 lectures, but there will be a short homework assignment due next Monday. Okay, so there's going to be probably, I don't know, 1 or 2 problems due next Monday. It's going to be on this material, which we saw at the end of lecture 8. For a little bit, I'm going to give more detail and some more applications of this. Okay? Okay, so let me remind you of the setup for defining this adjacency matrix. So we had a graph, gamma. Okay? So this was just vertices, edges between them. I think we had kind of different settings in different lecture videos. So I'll say one thing here. You can do this completely generally, actually, where you're allowed to have multiple edges between vertices is allowed. And also loops are allowed. Okay? At this point, we're fine. At some point, you can also add directions, okay, but I won't do that just yet. Okay, so you can label all of these edges so that, and you think that the edge goes from, V1 to V2 instead of the other way around. Okay, so far I'm not going to label anything. All right, and then we defined an adjacency matrix. Okay, so this is an n by n matrix where n is the number of vertices. And the ijth entry, aij, is the number of edges going from the ith vertex to the jth vertex. Okay, and we're allowing multiple edges and loops. So this would be this, like, for example, on the vertex 1 would correspond to 1 in the 1, 1 slot of the matrix. Okay, so you do see some, if you allow these loops, you're allowed some terms in the diagonal. Okay, so that's kind of what you see here. If you saw multiple edges between, then this would translate to a 4 here and a 4 here, where this is the ith, jth, and jith slot. Okay, sorry, so this is ij and ji. Okay, so for vertex I and vertex j. Okay, if there's no edges between, then we get just a 0 there. Okay, so A is a real symmetric matrix. Okay, we're assuming that the graph is not directed. Okay, there's a version where you have directed edges and then you only count, then it wouldn't be symmetric anymore. Okay, you would only count things that go from I to j and not vice versa. Let me just remark at this point the trace of A. Well, this is the terms down the diagonal. The diagonal terms correspond to loops. So this is just the number of loops in the graph gamma. Okay, so if you saw a graph that looked something like this, you would have a trace of 2. All right, and we saw a little bit of this at the end of the last video, okay? So this was the fact that the adjacency matrix is going to determine the number of walks between various vertices. So let me just make this a little more formal. So a walk in the graph of length L between vertices U and V, okay, is a sequence. All right, so I'll write it this way. U is V1, then we have E1, V2, E2, V3, and so on until we get E, L, VL equaling V, okay? Oh, this is probably VL plus 1, okay? So we have a sequence of vertex, edge, vertex, edge, vertex, edge, and so on, and it's a walk on the graph, so you can guess what it means. Well, the vertices are vertices of G, the edges are edges, and the vertices of the edge, EI, are VI and VI plus 1. Okay, so in other words, you have V1, here's E1, then it goes to V2, here's E2, it goes to V3, and so on. They can repeat, they can go over each other, you know, you can just go out and back. The only thing that matters is that you use, well, exactly L of them, so L edges, and then you start at U and end at V. Okay, so let me state a theorem, which I did state, I think, in the last lecture, but I'm going to give kind of a more rigorous proof, or hopefully a rigorous proof, okay? So for any natural number, okay, the ijth, or maybe I'll call this n, the ijth entry of the matrix A to the n, okay, so the n-fold product, is equal to the number of walks from vertex I to vertex J in the graph of length exactly L. Okay? So the way that you can calculate the number, so if I have a vertex here, I want to know all the possible, you know, path walks of length 1,000 that go from here to here. Then you can calculate that by going to this matrix, calculating a high power of it, or whatever power you want, and then that gives you, and then look at the ijth entry. Okay, so let me give a more careful proof of this, okay? So the proof, maybe unsurprisingly, is by induction on n, okay? So for n equals 1, this is clear, right? So the ijth entry is the number of edges between, say, Vi and Vj, okay? And this is equal to the number of length 1 walks, okay, from Vi to Vj. Okay, so for any vertex, we get, or any pair of vertices, you look at the number of edges, that's the number of length 1 paths, okay, so that's it. Okay, so now we assume it's true for k, okay, so if we look at the ijth entry of a to the k, we can compute the ijth entry. Entry is the number of paths, or I keep saying paths, walks, Okay? And now you want to show it for k plus 1. Well, let me draw a picture. So we have vertex I. Here's vertex j. Okay? And you want to compute the number of k plus 1 paths. Well, suppose you have a path of length k plus 1. I don't know, might look something like this. All right. Well, we know that the length k, so if this is a path of k plus 1, we get a path of length k between vi and a neighbor of v sub j. Okay, so v sub j might have many neighbors, right? So there might be another path going on of length k plus 1 over here. It'll have a fixed set of neighbors. And this is exactly how to count the paths of length k plus 1, right? So the paths of length k plus 1, okay, I guess I switched from walk to path. I can't help myself. So the paths of length k plus 1 between vi and vj are in one-to-one correspondence between paths of length k between vi and neighbors times, well, the number of paths between vj and its neighbors. Right, so I might have to, let me just add to this picture, okay? If I had two edges here, right, then multiple edges here, then of course if I had a path of length k, which got to this neighbor, I would have 3 different ways to get to vj, so this path of length k would count twice, okay? If I had a unique path, then it would just be 1. But in general, you have to take every path of length k between vi and its neighbors and multiply it by the number of paths between vi and vk. Well, this, notice, is exactly the blank jth entry of the adjacency matrix. Right, this is exactly what the adjacency matrix is counting, number of paths between vj and its neighbors. On the other hand, these are exactly the I blank entries of the adjacency matrix A to the k by induction. Okay, so it's not all the entries because I'm only counting the ones where these are the neighbors. Of course, if you have a path of length k that doesn't go to a neighbor, this gets multiplied by 0. Okay, so I could have just said these are the path of length k between vi and any vertex, and then times the number of paths between vj and that vertex. Sometimes you get 0. Okay, so and this is by induction. Okay, and now how do we get matrix, the ijth entry of the matrix A sub k plus 1, which is equal to A sub k times A? Okay, well, the way that you derive this is you take the sum of the AIL times ALJ terms. Let me just emphasize this is in A to the k, this is in A, all right? And now this, when you're taking this sum over all L, so all vertices, you're exactly corresponding to this. So this A is counting the number of paths here. By induction, this A to the K is counting the paths here. Okay, so it's kind of this nice miracle, or feels like a miracle, of matrix multiplication. You've set up the matrix in exactly the way so that what matrix multiplication is doing is extending out a path of length k to a path of length k plus 1 in all possible kind of directions. Okay, so that's the proof. So let me give you kind of some corollaries or special examples of this. So here's like kind of a nice corollary, is that an adjacency matrix detects whether a graph is connected. Okay, it's something which is immediately not really clear to see from the matrix, right? But if I take some, I don't know, graph that looks like this, okay, so it has many pieces. Well, if I take the matrix A, I can't detect immediately, from this graph that it's connected, or from the matrix. On the other hand, if I take high powers of A, they will always have zeros in certain slots, right? So no matter if this is vertex 1 and this is vertex 2, then there will never be a non-zero entry in the 1, 2 coordinate just because there's no paths that go from here to here, okay? On the other hand, so this is a contradiction, okay? And this does not happen for connected graphs. Okay, so if your graph is connected, then there will eventually be a path between any two vertices of some length, which means that eventually the adjacency matrix will have all positive non-zero entries. Does not happen for connected graphs. Okay, so another corollary, just a special case, is that the trace of the matrix A to the K is just equal to the, the number of loops in gamma of length k. Okay? So for example, the trace of A cubed would be the number of triangles. Okay, so if you want to take your graph and look at how many triangles there are going through any possible vertices, maybe, I don't know, okay, my graph will have a lot of triangles, looks something like this, then the trace of A cubed will count that, okay? You have to be a little careful in general because if you take, say, like the trace of A to the 4, it's not really the number of rectangles in your graph. Because notice this is picking up paths that just go like right back there. Okay, so it's kind of a trivial rectangle. It doesn't pick up a path of length 4 with distinct vertices. Okay, that's just part of the, that's a drawback of taking this matrix. I mean, sometimes you're only interested in paths and graphs that are more non-trivial than that. Let me give you now just a remark. You can do the same for directed graphs. Oops. And the same result applies. Okay, so if I take something like this. So now my adjacency matrix will be just 1, 1, 1, 1, okay, because we're only allowing walks that go along the edges, or in other words, we're only counting neighbors if you can get from vertex 1 to vertex 2, or vertex 1 to itself along an edge labeled the right way. Finally, another remark, we can do the same for weighted graphs. Okay, so here I was thinking all of my edges are length 1, or weight 1. In a lot of applications, you actually want to measure, I'll just draw the same picture as before, you actually want to measure some sort of distance or difficulty of getting between each vertex. All right, so this might be, you might put 1.2, 2.5, 3, 1, okay? And then the adjacency matrix is just the same thing, okay? So when you go along this path, you're now doing, you've added 2.5, so if you go, I don't know, so this is would be a length of 6.5, all right? And the adjacency matrix is you just put the weight on the slot. Okay, so here the matrix would be 1, 1.2, 3, 2.5. Okay, so this is if you want to get from vertex 1 to vertex 2, oh, I hope I did this right. You're supposed to go along 1.2, but it takes 3 to get back. Okay, and then you can ask for, if you want to count the number of paths of weight, less than 1,000 or something, then you can work that out. All right. Okay, so let me maybe I'll stick to non-weights for now. Okay, so I want to go to this example again. What this brings up is an issue naturally. Okay, of wanting to compute traces of large powers of matrices. Okay, so you might say, well, actually what we need to do is not just the trace, is the ijth entry. Okay, it'll turn out that the trace is a lot easier, which is why I want to do this. Okay, so ijth entries are harder. Okay, kind of magically. Okay, so, but this is, what we'd like to do is I want to take this matrix and I want to say, how many loops, so just paths starting and beginning at the same vertex, how many loops are there of length, 1,000? Okay, how can I figure this out in an efficient way? All right, so let me give you two kind of ways to compute the trace of this matrix, or the trace of a to the 1,000. Okay, that's what we really want to figure out. Okay, so there's kind of two things you can do. The first way is more specific to this matrix. Okay, and it will also, and in this case, it will compute the entries. Okay, so how to do this for 1, 1, 1, 1. Okay, so we'll give you specific way for this and then apply it to a more general way. It ends up using a little more machinery, but it's more useful in general. Okay, and some of this machinery we're just going to see later in the class. All right, so how would you want to compute, say, 1, 1, 1, 1 to the 1,000? Okay, so first notice that, well, what does 1, 1, 1, 1 do to a vector xy? Okay, well, this just goes to x plus y, x plus y. Okay, so in other words, it takes any vector, and the important thing here is that it takes any vector in R2 and sends it to a vector with equal x and y coordinate. Okay? So in other words, the image of this transformation, thinking of it as going from R2 to R2, is this diagonal, right? So all of R2 gets sent to this diagonal. On the other hand, you know what this matrix is doing restricted to the diagonal subgroup, okay? So no, or the diagonal entry. So now we have A, right? So if I go from R2 to R2 and I do A squared, well, first A takes me to the diagonal, second A takes me again to the diagonal, and now I just have to understand what A does to diagonal elements to figure out this part. Okay, so if I put in 1, 1, 1, 1, let's say AA, well, of course, this goes to 2A, 2A. All right, so now I know what to do. So the first A, okay, takes me to the diagonal. The second application of A, and all further applications, application of A, and third, fourth, etc., take the vector to twice the vector. Okay? So in other words, if I want to see where 1, 0 goes, well, 1, 0 goes to 1, 1. Then this goes to 2, 2, 4, 4, and so on. So this is going to go to 2 to the, I guess, 999, since I did 1,000. And the similar thing for 0, 1, right? 0, 1 goes here, and then tracks on the same rate as 1, 0. Okay, so this is kind of a matrix where it's easy to multiply, matrix multiplication iteratively. Okay, this is kind of a special case, right? You're taking a matrix to a one-dimensional subspace. Right, so the image is one-dimensional. Special case, the image of A is one-dimensional, and we know how it behaves, how A behaves on this one-dimensional subspace. Well, that's not too special, but certainly the image being one-dimensional is quite a special fact. Okay, so if A was an invertible matrix, this method wouldn't work. It'd be much harder to apply, but we can find the matrix in this way. Okay, and then here we get every entry. Okay, so we know if you want to work out the number of paths of length 1,000, maybe I will just go back to here. So if you want to figure out the loops of length 1,000, well, it's 2 to the 1,000 minus 1. And you should think, if I'm following along this graph, maybe I'll try to draw the different color, oops, that's not the right thing. At every stage, I have exactly 2 choices, right? I can go here, or I can go here. And then wherever I'm at, either I go here, or I go here. So there's 2 choices every time. It's not too surprising that you end up with something like a big power of 2. Okay? All right, so that is the special case, but let me compute this answer, at least a trace of it, in another way, and that will let us work more generally. Okay, so another way. Well, here we have to write A as a product of matrices. Okay, so I'll write this at 1, 1, 1, 1. Okay, so notice the image is one-dimensional. And on that subspace, A acts by multiplication by 2. Okay? And now you should think, well, what is another matrix? A simpler matrix, which has one-dimensional image, and on that subspace acts by times 2. Well, it's going to be 2, 0, 0, 0. Right? This has one-dimensional image, and namely the x-axis, and on the x-axis you multiply by 2. And what we want to do is do a change of basis, which takes this subspace to this one. And in particular, what we want to write is A is some matrix P inverse times this matrix. Now notice this has, so I'm going to say this is what we want. Why do we want this? Well, then notice A to the K is just P 2, 0, 0, 0, 2 to the K, P inverse, right? This is because if I take, okay, I'm going to shorten this to D, okay? So if I take PD, P inverse to the K, this looks like PD, P inverse, PD, P inverse, P, T, P inverse, and so on. I think you get the point. Now these inverses go to the identity matrix, so we can cancel them. So you just get P, D to the K, P inverse. Okay? On the other hand, you now get that the trace of A to the K is the same as trace of D to the K. Okay, and this is because we're comparing, this is, as we worked out, this is D to the K P inverse. Since trace of AB is trace of BA, I can swap these. So I get P inverse D to the K, and that's what I want. Okay? So, no surprise, the trace of this one will be 2 to the 1,000. Here we got 2 to the 999 plus 2 to the 999. So we got 2 to the 1,000 again. Okay, so the answers worked out. Okay, so how do you, well, I won't go into how to find this matrix. Okay, so finding P, so it's similar to finding these change of basis matrices that I've talked about. Will be coming soon. Okay, an exact description of how to find them. Maybe I'll just, since you believe me, I'll write this as 2, 0, 0, 0. And you can check if I put 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, negative 1 over square root of 2. And then I put, well, here should be the inverse. And we know the formula for these. Okay, so I think I did that right. Something like this. Then this is precisely going to be 1, 1, 1, 1. Okay, so that's the general strategy for finding the trace of large matrices, especially if you can't find an explicit formula for the matrix, like in this case. Okay, so this is like a pretty good, time to write examples or just things for you to play around with. Okay, so I would, try like a 3 by 3 matrix, which looks something like this. You can also try 2 by 2. For some of these, you can maybe try to find a diagonal version of it or work out explicitly, what the powers of some matrix are, so then you can find exactly how many paths of length, blah. Okay, so this is you try. Another kind of class of examples which you can kind of play around with? Well, you can look at things like bipartite graphs. Maybe like complete bipartite graphs. So you take two sets of vertices between every pair of vertices, one from one set here and one from another set here. So let's say I'm missing one, I think. Okay. And another good example is the complete graphs, which just have some number of vertices and all the edges between every possible pair. So, you can look at like something like this. Complete graph on 3 vertices as a good example. So in these cases, you can work out the number of paths just, by kind of thought. I don't know why I put that in parentheses, but okay, or in quotations. But that's essentially, if I ask you, here's a vertex in a bipartite graph, how many paths are there to get, of length? Well, first one would be like of length 3 that come back and end at this vertex. There should be 0, and you can work out the general formula quite easily. And then this tells you something about the adjacency matrix. Okay, so something about the adjacency matrix A. Okay, so you can think about just this 3x3 example if you'd like, or the complete graph on 3 vertices. You should be able to easily tell how many paths there are, which start and end at V and are of a certain length. That tells you something about taking high powers of the adjacency matrix, again without having to compute. Okay. So I think I will stop there, or stop here. Maybe I will just advertise for now kind of a great resource. There's a number of resources on this, but if you look at Richard Stanley Topics in Algebraic Combinatorics, this is where I'm kind of sourcing this material from. I'm not exactly sure what section it is, but if you search for this plus adjacency matrices, I think you'll probably find it. So this is from a course at MIT. In any case, there's just a whole bunch of material here, and he's one of the best people to read it from. So, okay, I will stop here and have a good one.